questions which were there in this particular question paper. And the subjects that we are covering right now is thermodynamics, its application, and heat transfer. So let's get started. So this is the first question that we have. The question says that an aluminum ring of mean diameter of 5 meter at an ambient temperature is clipped into liquid nitrogen. So we have a ring, imagine a ring which is at an ambient temperature, and this ring you are basically dipping into liquid nitrogen bath. Okay. And what will be the mean diameter of the ring in the liquid nitrogen bath? Coefficient of linear expansion of the aluminum alloy in the temperature range may be taken as 20 into 10 to power minus 6. Ambient temperature may be taken as 24 degrees. Boiling temperature of the liquid nitrogen is 77 K. So basically, understand this, ring is at a higher temperature. Okay, it's at 24 degrees C. As soon as you dip the ring into the liquid nitrogen, basically what will happen after a long period of time, the ring is going to acquire the same temperature as that of the liquid nitrogen. Okay, so what will happen? Heat transfer will happen, and the liquid nitrogen is going to basically reach to a boiling temperature. Okay, so how do we solve this problem? So let's look at it. So basically, you have this ring. Okay, this is the ring that we have. Diameter of the ring is 5 meter. Okay, now we take this ring. This ring is initially at an ambient temperature of 24 degrees. Okay, we are dipping it into liquid nitrogen bath. Okay, okay, boiling point of liquid nitrogen is 77 K. Okay, so as soon as you dip it in the liquid nitrogen, right, what is going to happen? The ring is at a higher temperature. It will transfer energy to the liquid nitrogen. Okay, and it will keep cooling down. So this is a cooling process. Okay, so the ring is eventually going to cool till 77 Kelvin. Okay, and 77 Kelvin, if you convert it into degree C, it's basically a negative temperature. That what you are going to get. So the ring is going to contract. So how do we get the answer? So we use simple relations. So we know that what is the strain? The thermal strain, if you want to write it like the thermal strain, is nothing but change in length by original length. Okay. So what is the change in length of the ring? So I can say pi times d2. This is the final diameter minus d1, which is the initial diameter, divided by the initial length of the ring, which is pi d1, is equal to alpha times t2 minus t1. Okay, let's simplify this. What do we get? We get d2 by d1 minus 1 is alpha times t2 minus t1, and we get d2 as d1 bracket 1 plus alpha times t2 minus t1. Okay, what is d1? D1 is 5. Okay, alpha is given as 20 into 10 to power minus 6. Final temperature of the ring will be 77. It will come in the same thermal equilibrium with the liquid nitrogen. And initial temperature of the ring is ambient temperature, 24 degrees. If you convert it into Kelvin, 273 plus 24, you are going to get 297 Kelvin. So if you substitute here 297 and solve this problem, you are going to get final diameter as 4.978 meter. Let us look at the option, which is matching this answer. So option is option A. Okay, let's go to the next problem. Next problem is related to the pure substances, probably you could say. Okay, so it's basically a problem which is talking about the phase. It's talking about the phase diagram. Okay, so what it says: vapor pressure in mm of mercury of solid and liquid ammonia is given by the expression. So we have two expressions. What is being asked is to find out the triple point of what. So let's draw the PT diagram, and probably then the answer becomes very clear. So if we draw the general phase diagram, that is pressure versus temperature diagram. So how this diagrams look like? So you first have the curve. This curve is basically your sublimation curve. Okay, then you have the vaporization curve, and then you have what is called as the fusion curve. So this is your fusion curve, this is your vaporization curve. Okay, and this point, so here what you have, this side of the curve, the substance will be in the solid phase. This side of the curve, the substance will be in the vapor phase, and in between it will be in the liquid phase. Okay, so this is our sublimation curve, this is our vaporization curve, this is our fusion curve. And this point where all the curves intersect with each other, this is called as the triple point. Now, what is given to us? It is given to us, he has given us two equations. One equation for one curve, okay, for the solid and liquid ammonia, and the second curve is also given. Okay, so at the triple point, what do we get? All the three phases are in equilibrium, so pressure should be same. Okay, whatever pressure we get there, it should be same, so we can equate these two equations, okay, to find out what is the temperature. Okay, so you can equate 23.179490 T. Okay, this should be equal to 19.6 minus 3049. So what we are trying to find out, basically the point of intersection of these two curves, which will be nothing but triple point of the substance, that is ammonia. And solving this equation, we will be able to predict what will be the temperature at the triple point. So 23.1 minus 19.6, you can substitute this, solve this problem. Okay. If you solve it, you are going to get 700 divided by 3.5, which is 200. Okay. A simple logic. We have been given equation of the two curves. Okay. We know at the triple point, all the phases they coexist in equilibrium, and triple point is nothing but the point of intersection of these curves, and we use that fundamental to find out what is the triple point of this particular substance, which is ammonia. So answer is C, 200 Kelvin. Let's move to the next problem. What is the entropy change when water is vaporized at 100 degrees C? Latent heat of vaporization of water may be taken as 2238 kilojoule per kg. Very simple problem. Let's draw the TS diagram. Okay. If you draw the TS diagram, things will become very simple and you will get answer very quickly. Let's draw the TS diagram. Okay. So this is the TS diagram. Let's draw a constant pressure line on the TS diagram. So this is a constant pressure line on the TS diagram. This line is the saturated liquid line. Okay, this line is the saturated vapor line. Okay, and this point here is our saturation temperature, which is basically 100 degrees. Okay, so vaporization, if I have to talk about, so probably we are at this point, which is in the liquid state, water is in the liquid state, and at this point, the water will be incomplete in the vapor state. So when we are talking about the vaporization process, so probably we are talking about a constant pressure process when the state of the water changes from state 1 to state 2. Okay, so we know from basic thermodynamics, so what is our dq for a reversible process? Let us say dq is tds. Okay, dq is tds, right? That's the basic thing. Okay, and what do we get here? So q is t saturation divided by sg minus sf. Okay, now we know tds. One more equation we can use, which is dh minus nu dp. Okay, this is the second equation which we can use. So for a phase change process, pressure remains constant. So if pressure is constant, so dp will become 0. So what do you get? tds is dh for a constant pressure process, because phase change is a constant pressure process or pressure remains constant. Okay, so if I integrate this state from state point 1 to state point 2, this the temperature in that change of state remains constant, which is our saturation temperature, Ts. This will be Sg minus Sf, nothing equal to Hg minus Hf. And we are supposed to find what is the entropy change, which is Sg minus Hf. Sf will be Hg minus Hf divided by T saturation. Okay, and Hg minus Hf is Hfg, which is the latent heat of vaporization that is given to us. That is 2238 kilojoule per kg. Saturation temperature is 100 degrees C. Convert it to Kelvin, it is 373. If you divide it, you will get an answer 6 kilojoule per kg. Answer is C. It's a simple application of, you apply the TDS equation. Okay, the second TDS equation, which is here. And since the phase change is a constant pressure process, which we are talking about, just integrate the equation between the two to find out the change of state. You will get this answer. So answer is C, 6 kilojoule per kg Kelvin. Let's move to the next problem. Examine the following statements. Work is a high grade of energy. Yes, when we study the topic of availability in thermodynamics, so we know that we classify energy into two categories: high grade energies and low grade energies. So mechanical work, electrical energies, they are classified as high grade energies, whereas thermal energy or heat energy is classified as low grade energy. So work is a high grade energy. This is a true statement. Okay. Second thing, it is possible for a heat engine to produce work in a cycle by exchanging heat with bodies at same temperatures. So it's not possible actually. So let's say if you just imagine that you are having a heat engine, okay, you are having a heat engine, and the temperature of the source and the sink, they are same. Okay, that's not possible. Basically, you need a temperature difference. In all the heat engine that we have studied in thermodynamics, be it reversible or irreversible, we have seen that whenever we need or whenever we produce a network, how does we produce a network in a heat engine? Basically, in heat engine, basically it is taking energy from a source or a high temperature energy source. It takes the energy, a part of that energy it converts to work, and the remaining part of the energy is rejected to a low temperature sink. So we see that between source and sink, there is a temperature difference whenever we are trying to define a heat engine. So this statement is a false statement. When both are at the same temperature, we cannot produce a network. Okay. Third statement. It is possible to construct a device while operating in a cycle. It is impossible to construct a device which is operating in a cycle will produce no work other than the transfer of heat from a cooler to a hotter body. This is a correct statement. This is basically the Clausius statement, basically. And Clausius statement says that if you want to transfer energy from a low temperature sink to higher temperature, okay, if you want to do this operation, then you have to provide certain amount of net work. Okay. So this is basically forms the principle of our refrigerators. This forms the principles of heat pump. In refrigerator, what do? We are trying to maintain some space at a lower temperature as compared to ambient. So we are extracting energy from a lower temperature and transferring energy to a higher temperature, which doesn't happen by itself in nature. In nature, always heat or energy gets transferred. Heat get transferred from higher temperature to lower temperature, okay, by itself, which is a spontaneous process. But here we are trying to if we want to transfer heat from low temperature to high temperature, it will not happen spontaneously, okay, or it's not going to happen, okay. So in that case, you have to provide a certain amount of network, okay. So this is basically the Clausius statement, okay. So this is a true statement here. So if I look at the options, so option 1 is right and option 3 is right. So let's look at the correct option when we look at all the things. So all statements are wrong. This is not the right thing. All statements are correct. Not option number 1 and 3. These are the correct option. So option is option C here. Statement 1 and 3 are correct. Okay. Let's move to the next problem. Molière diagram. What is Molière diagram? Again, a problem from the basically properties of pure substances. Okay. So what is Molière diagram? What is the principle? So if you write the second TDS equation, which is TDS is equals to DH minus nu dP, and let us say you consider a constant pressure process where pressure is constant, what do you get? You get TDS equal to DH, okay, or you get DH/ds at constant pressure equal to temperature. This equation is the basis for forming a particular diagram, which is basically called as the Molière diagram. So in the Molière diagram is nothing but it is an enthalpy entropy plot, okay, which is something like this. And what this equation is saying, dH/ds at constant pressure is equal to absolute temperature. So if you find out the slope of enthalpy with entropy in the phase change region, the slope will be constant. Beyond that, the slope will increase. So if you have a two constant pressure lines, those lines are going to diverge in a Molière diagram. So Molière diagram is nothing but it is an enthalpy entropy chart. Okay, so the option is option D. Let's move to the next problem. Okay, so this particular problem, what it says the real gas behavior approaches the ideal gas equation when. So in thermodynamics, we have extensively used ideal gas approximation in while solving number of problems. But we know that the ideal gas equation is basically a model for modeling the pressure, volume, and temperature behavior of the gases. Okay. But this model, it's not valid for all pressure, temperature, and volume conditions. Okay. It actually replicate the behavior of the gases under very restricted kind of conditions. Okay, under very restricted kind of conditions. Which are those conditions? This condition is the condition when your pressure is very very low and temperatures are very very high. Okay, so you know the answer is answer D. Here answer is D, but we'll explain here. So we know that the ideal gas equation is nothing but P nu equal to RT. Okay, so this is the ideal gas equation. So in order to correct the behavior of the ideal gas, so basically ideal gas is nothing but it is a relation between pressure specific volume, and temperature. So this model gives the relation between pressure, specific volume, and temperature of a gas. This model, we call it as an ideal gas model. But this model is not a true representation of the gas. Okay, so in order to correct that, you basically introduce a factor which you called it as a compressibility factor Z. Okay, and Z is nothing. This is P nu by RT. So Z basically tells you, it is basically a deviation factor. How much your behavior of the gas, it deviates from the ideal gas. So Z is basically a factor which tells you how much is the deviation. If Z is equal to 1, you say that the actual gas behavior approaches the ideal gas behavior. If Z is away from 1, you say that the actual gas behavior deviates from the ideal gas. Okay. And I'll little bit explain this in detail slightly. So if you plot, basically you will see a plot which explains this. So if you plot basically your Z, which is basically the compressibility factor, which is P nu by RT, with PR, which is nothing but reduced pressure. PR is nothing but actual pressure divided by the pressure at the critical point. Okay. So if you plot on this different reduced temperature lines, where reduced temperature is defined as actual temperature divided by the critical temperature. So you will see the Z value of Z here is 1. Here the value is 0.1. Okay. PR is 1 here. So you basically see this kind of behavior. At TR, this value will be TR equal to 2, and this value will be TR equal to 1. So you see, at lower pressures, when you have lower pressures, when you move to lower pressure regimes, irrespective of the temperature, your Z is approaching 1. So at lower pressure, irrespective of the temperature, Z approaches 1. So you can say at low pressure, your ideal gas approximation is good enough. Similarly, at higher temperatures, you can see at higher temperatures, this line is almost like a higher temperatures also, your Z is 1 for this line. So under these two conditions, you can assume the behavior of the real gas to be equivalent to the ideal gas. That is at low pressures and at high temperatures. So that's why the option is answer. Option is the option D. Answer is D here. Let's move to the next question. For water, the latent heat of freezing is 334 kilojoule per kg. Specific heat averages as 4.9 kilojoule per kg Kelvin. Quantity of heat removed from 1 kg of water in order to turn it into ice. So basically what we have here, just look at it, this problem. So you have here 1 kg of water. Okay. This 1 kg of water is at 30 degrees C. Now what you are doing, you are removing heat from here. Okay. So as you remove the heat from the water, what will happen? So this is water. So as you remove heat from this water, okay, what you will get? You will get water at 0 degrees C. Okay. So you are removing heat. So as you keep removing heat, the water temperature will decrease and it will reach 0 degrees. Once it reaches 0 degrees, after that what is going to happen? Then this water will get converted into ice at 0 degrees. From 30 degree to 0 degrees, what you observe? There will be nothing but there will be change in temperature. Okay. So as you are removing the heat from the water, there is change in temperature. So this heat transfer, which is happening from, let us say, state 1, this is state 2, and this is state 3. From between state 1 and 2, the heat transfer that is happening, that heat transfer is called as sensible heat transfer because it leads to change in temperature. Okay. And the heat transfer that happens at constant temperature and leads to the change of phase, this heat transfer is called as the latent heat transfer. So if you want to calculate the total heat which is being removed, the total heat will be, you have to calculate Q sensible plus Q latent. Okay. So Q sensible is nothing but m CPDT. So mass m, which is 1 kg, let us say C into delta T, which is how much? 30. So let me just write the values. This is sensible. So we'll write here Q sensible will be m CPDT. So m is 1, C is 4.19, delta T is 30. Q latent is how much? This is 334. Okay, so the total heat that needs to be removed is how much? Let's calculate this. This will be 459.7 kilojoule. So answer is option D here. Let's move to the next problem. Okay, so here this problem is talking about the Stirling cycle. I think there is a issue here in this particular question that we have given here. The actual, there is some kind of a typo which I am seeing in the PDF here. The actual option, which is option 1, is something which I will plot here right now. The actual option for 1 is this here. That's a PV diagram, and the actual option is this: 1, 2, 4, and this. So this is not the actual option. This is actually if I have to say these are two, so this is repeated 2 times. So this is the actual option 1 in the examination paper. Okay, so which is basically your PV diagram. Okay, this is option 2 and 3 and 4. So here what we are talking about is the Stirling cycle. So what is a Stirling cycle? Let's look at what constitutes the Stirling cycles. So one option, if you look at option 1 and 2, this relates the PV diagrams. Okay, so this is talking about PV diagram. Let's move to the next option. Option 3 and 4 are talking about the TS diagrams. Okay, so let's look at it. What is a Stirling cycle? So in the Stirling cycle, basically, when you look at it from thermodynamics point of view, how many processes we have? So in the Stirling cycle is basically made up of 4 processes. Okay, so we have one process which is a constant temperature process. The temperature remains constant. So this is a constant temperature expansion process that we are talking about. This is process 1, let us say, one of the process. Another process is volume equal to constant process, which is also called as a regeneration process. Basically, process C, or third process, is basically again constant temperature compression process. Okay, and fourth process is again a constant volume regeneration process. In the process 2, which I am calling as a regeneration process, here the working fluid, it transfers heat to the regenerator, so it loses that heat. And in the process D, which I am talking about, the regenerator, it gives back heat to the working fluid. So these 4 processes, it constitutes the basically Stirling cycle. So if now we try to draw the PV diagram, so what is the PV diagram? Let's look at the PV diagram here. Okay, so process 1 to 2 is your constant temperature compression process. We know Isothermal process is nothing but PV equal to constant in a PV diagram. So this is constant pressure compression because your specific volume is decreasing. Then we have constant volume process, which will be 2 to 3. So here volume remains constant. Then we have 3 to 4, which is again constant temperature expansion process, which is zero point 0.4. Why expansion? Because your pressure is decreasing and volume is increasing. And 4 to 1 is again constant volume process. So this is the PV diagram of the Stirling cycle. Similarly, let's try to plot the TS diagram. If we plot the TS diagram, first we have constant temperature, heat rejection, let us say. So this is the constant temperature process 1 to 2. Okay. Then we have a constant volume process. So you know in TS diagram, the constant volume lines, they go like this. Sorry. I'll just expand it here. This is your constant volume line. And then there is a constant temperature process. Okay. And then again, constant volume process. So this is temperature equal to constant, temperature equal to constant, and specific volume equal to constant. So this is the PV diagram for the Stirling cycle, which constitutes of two constant temperature process and two constant volume process. This is the TS diagram for the Stirling cycle. So let's look at the options. We'll go to the previous pages. Okay. So PV diagram, option number 1 is correct. Option number 2 is wrong. Okay. TS diagram, option number 4 is correct. So option, which is the right option? Option number C, we have first and fourth here. Okay, so that's the correct option. Let's move to the next problem. Okay, so now this is basically a refrigeration problem that it is talking about. He's saying what is the power of 2 ton of refrigeration system? Latent heat of ice is given. Okay, so basically we know the tonnage of refrigeration system, how it is defined. So 1 ton of refrigeration, how we define 1 ton of refrigeration? 1 ton of refrigeration is nothing but, let us say you have 1000 kg of water. Okay, 1000 kg of water at 0 degrees C, and you want to convert this water which is at 0 degrees C into ice. How much heat you have to remove it from this in 24 hours? Okay, so as to convert this 1000 kg of water to ice. That is how you define 1 ton of refrigeration. So 1 ton of refrigeration is what? It is you are trying to convert 1000 kg of water, okay, 1000 kg of water into ice. So how much heat is removed? So this is a phase change process. Water from 0 degree is getting converted to ice into 0 degrees. So it will be 1000 mass times the latent heat. Latent heat is 336. So this is the total energy. And how much energy we have to remove in 24 hours? So 24 divided by 3600. So this is the rate at which you have to remove the energy. And this value is defined as 1 ton of refrigeration. He is asking us what is 2 ton of refrigeration. Just multiply it with 2. So it will be 2000 into 36 divided by 24 into 3600. If you solve it, you get 7.7 kilowatt, which is option A. Okay, let's move to the next problem. Okay, what we have here, we have an Otto cycle. An air standard Otto cycle operates with a compression ratio of 9 with ambient temperature of 300 Kelvin. If the adiabatic index of the medium is 1.5, what is the efficiency? So what is an Otto cycle? We already know if you draw the PV diagram. So you can clearly see what is an Otto cycle. So we have a constant pressure compression, constant reversible adiabatic compression, constant volume heat addition, then reversible adiabatic expansion, constant volume, heat rejection. These are the four processes which makes the Otto cycle. Okay, this is the volume that we have at this volume we call at the volume at BDC, and this is the volume which we call as the volume at TDC. How do we identify BDC, TDC? Just imagine the piston cylinder arrangement. This is the volume at this point, which is defined as the top dead center when the piston reaches at this position. And this is the point which is defined as BDC, which is the bottom dead center when the piston is at this position. So let's draw the piston for time being. So when the piston is at this position, the total volume is V1. When the piston is at top dead center, the volume is V2. Compression ratio is nothing but V1 by V2. Okay. Efficiency of the Otto cycle is 1 minus 1 divided by R, which is compression ratio, raised to power gamma minus 1. Gamma is your adiabatic index. Okay. So you take this 1 minus R, which is 9 divided by 0.5. If you calculate this, efficiency comes out to be 60. Let's see how much it comes out. It comes out as 0.5. So it comes out as 66.67%. Answer is option number B. Let's move to the next problem. Okay, so now we have the Carnot refrigerator. Okay, so let's draw the, sorry. I will take an eraser for timing. I'll just erase it. So we have a Carnot refrigerator. Let's draw the refrigerator first. Okay. A simple schematic of the refrigerator. So basically you have a refrigerating space. Okay. Or so this is your refrigerating space which you want to maintain at lower temperature. Okay. And this is your ambient where you are dumping the heat which you are extracting from this refrigerated space. In order to maintain this space at lower temperature, you need to operate a device in a cycle. So this is your refrigerator. Okay, so you extract the heat from the refrigerator space, okay, and you dump the heat to the ambient. In order to run this cycle, you have to supply certain amount of work. So this is your refrigerator. Now, what is a Carnot refrigerator? Carnot refrigerator. So we know the Carnot cycle, a refrigerator which runs on the reversed Carnot cycle, not the Carnot cycle, reversed Carnot cycle is called as the Carnot refrigerator. And if you define the COP, the COP of the Carnot cycle, or let us say COP of the refrigerator, it is nothing but a desired effect upon work input. Okay, so desired effect here is the cooling effect and work input is W. So if you apply first law of thermodynamics to this cycle, what do you get? You get QH minus QL is W. You can substitute here, you get QL by QH minus QL. Okay. This is the COP for the any cycle which is reversible or irreversible. Now COP for the Carnot cycle, how do we define it for the Carnot? So COP for the Carnot cycle is the temperature of the refrigerated space divided by the temperature of the ambient medium divided by the temperature of the again refrigerated space. So COP of the Carnot cycle, the reverse Carnot cycle. Okay. So what it is talking about? So we We have a temperature limit. How much? It is working from 270 to 300 Kelvin. And what it is saying is that between the same temperature limit, you basically have different cycles. Okay, different refrigerating cycles. Okay, between the same temperature limit. One cycle is using CFC as the refrigerant, other is using R32, third one is using ammonia. Which one is going to give the better refrigerant? Which refrigerant is going to give better COP? And we know that COP of the Carnot cycle, it depends only on the temperature of the medium. Okay, that is the temperature of, let us say, the refrigerating space, and the ambient that we are talking about, TH. It is independent of the working fluid. So if you have three refrigerating cycles which are operating between same temperature limits, okay, so all will have same COP. Okay, because they are operating between the same temperature limit. COP of the Carnot cycle is independent of the nature of the working fluid. So all will give same COP. Option will be option D. Okay, let's move to the next problem, which is identified as the coefficient of momentum transport. Okay, momentum transport. So probably options are given as density, kinematic viscosity, dynamic viscosity, and Reynolds number. Option answer is D, dynamic viscosity. And to understand it, we have a very basic problem. Let us say we always do like this. Let's say you have a fluid layer, which is the stagnant fluid layer, and suddenly, let us say on the top, you have a plate. Okay, on top of this plate, and then you move the plate with certain velocity v. So what do you observe? We observe that once we are moving the plate, okay, there is a velocity gradient that develops in this fluid layer. Okay, the top layer, it acquires the same velocity as that of the plate. Why? Because of a condition which is called as a no slip boundary condition. And the bottom layer, which is stationary, it remains stationary. And but in between layer, what you observe now, which were initially stationary, now they have acquired certain velocity. But how do they acquire this velocity? What is the mechanism by which they acquire the velocity? What is the property, fluid property, which is responsible for transferring the momentum from the top fluid layer to the immediate fluid layers? The property which is responsible for this transfer of momentum or transport of momentum from one fluid layer to the other fluid layer, it is basically your viscosity. Because of the viscosity, the top fluid layer, it will try to drag the layer which is immediately below it. So it imparts momentum to that layer, and that's how your momentum gets transferred from top layer to the next layer to the next layer. Okay, and you use this relation, simple Newton's law of viscosity, which says that the shear stress is nothing but mu du dy. What is your mu? Mu is the coefficient of viscosity, which is your dynamic viscosity, and du dy is the velocity gradient. Okay, so option is C here, dynamic viscosity. Let's move to the next problem here. So here, what is the problem? This is a heat transfer problem that we are talking about. Wall of a chemical plant is modified with two additional layers. Okay, so what it says is that, let's say initially you have, this is the wall of a chemical plant. Okay, now we are modifying this layer of the, or the wall of the chemical plant. How we are modifying it? We are adding two layers. Okay, so let us draw that layer. This is one layer, and this is the second layer that is being drawn. Okay, let us say the original layer, it was having thickness L and its thermal conductivity is K. So I will draw it here, K and L. Okay, let's understand it. Now what he is saying, the inner layer is half the thickness, This layer is half the thickness, L by 2. Okay. And outer layer is same the thickness. So outer layer is L. Okay. What it talks about thermal conductivity, let's read the first line again. The wall of a chemical plant is modified with two additional layer having half the thermal conductivity of the original material. So this thermal conductivity is K by 2 and K by 2. Okay. What it is asking is what will be the heat flow across the modified wall. Let's calculate the heat flow in the original wall. Let us say it is delta T by L by Ka, which is the resistance. Now calculate the heat transfer. It will be delta T, add all the resistance. So L by Ka, assuming Ka is constant and delta T is constant. This will be L by 2, K by 2 into area plus L divided by K by 2 into area. If you calculate, you will get delta T as 4L by Ka. Okay. So you can substitute K2 as 1 by 4 times K1. So what happens now? So if you look at K2, K2 is 0.25 times the K1. Because of the addition of these two additional layers, the heat flow across the modified layer will be only 25% of the original. Answer is option D, 25% of the original. Okay, so I think we have covered all the questions for the from the heat transfer and thermodynamic perspective. Thank you. Thanks for your time.